solving linear systems of equations. So, what is a system of equation? Well, it's two or more equations with the same variables. Usually we use x and y, but they could be any variables really. So, there are three methods we can use in solving the systems. These are common ones. You probably did these in Algebra 1, but it's a good idea just to refresh your memory. We can graph to find the system of equation, to find the solution. We can also use an algebraic method called substitution, or we could use another algebraic method called elimination. So the solution of a linear system of equations is the point of intersection. So where they meet, that's my solution. So in this first example, first we have to do is put them in slope-intercept form. That's the easiest way to graph. And then we'll see where that point of intersection is. So if I graph the first equation, my y-intercept is 0. I'm going to go up 1 to the right 2, up 1 to the right 2. Also go down 1 to the left 2, down 1 to the left 2. Get my line tool. Very, very carefully draw the equation of the line. Arrows on the end. Now, when we're doing this graphing method, we want to try to be as exact as possible. And we're going to do as many points as we think we need. So in my second equation, I have -2 as my y-intercept. Going down 1 to the right 2. Now I can see I'm going away from the line, so I can go the other direction. Up 1 to the left 2. There's my point of intersection right there. Up 1 to left 2. Get my drawing tool. Here's my line. Arrows on the end. So our point of intersection, where both those lines meet, is -2 and -1. Now the great thing about this is we can substitute it back into our original equations and see if we have the right answer. So I have x minus 2y, so I have -2 minus 2 times -1 is equal to 0. So it's -2 plus 2 equals 0. That works. So that point is on that line. Let's try the other line. So I have -2 plus 2 times -1 is equal to -4. -2 minus 2 is equal to -4, so that works. So I know that the solution I have of that linear system, that point of intersection, is correct. Okay, let's try another method. We're going to do some by substitution. So the first thing we want to do is we want to either get x or y by itself in either equation. So I have my second equation, getting that y by itself, looks like that's going to be the easiest one for me. So I have y is equal to -2x plus 7. Now, if you're in class with me, you'll hear me call this, I like to call this my revised equation. That's the one we're going to go back to, but I revised it from the original one. Now, everywhere I see y in my other equation, I'm going to substitute that in. That's why it's called substitution. So I have 5x minus 3. Now I'm going to substitute what I have. So the y is the same as -2x plus 7 is equal to 23. So I have 5x plus 6x minus 21 is equal to 23. So that gives me 11x minus 21 is equal to 23. 11x is equal to 44. So x is equal to 4. Now I need to find out what y is. We'll look up here. You can either go back to the original, or I do have y already set up in my revised equation. So I have y is equal to -2 times 4 plus 7. So I have -8 plus 7. So y is equal to -1. So here is my solution. Or if I were to have graphed these, it's my point of intersection. Now you could check this also. So I would really recommend this on a test. Substitute it back into the two original equations. And if you have get true statements for both, then you know you're all set. We're going to just save some time here, and we're not going to do the check step. All right, let's take a look at number 3. Same idea. I need to get x or y by itself. It looks like the easiest one is this y. I don't have quite y. I have -y, but that's okay. I can still, that's going to be the easiest one for me to work with of the ones that I have here. So I have -y is equal to 6x plus 27. Divide everything by -1, and I have y is equal to -6x minus 27. That's my revised equation. Go into my other equation. I have 3x plus 8. Now, everywhere I see y, I put negative 6x minus 27 is equal to 9. So I have 3x minus 48x minus 216 is equal to 9. Gives me negative 45x minus 216 is equal to 9. Negative 45x is equal to 225. And x is equal to negative 5. Now again, my revised equation. Everywhere I see an x, I'm going to put a negative 5. So if y is equal to 30 minus 27, so y is equal to 3. So my solution to my linear system is negative 5, 3. And again, if you were to graph that, that's where they would intersect. All right, let's look at our third method. Solving by elimination. This is my favorite one. I like using this one. So what we're trying to do is we're trying to eliminate one variable by adding. So if you look at number 4, we have 3 problems here, each of a different level. So if you look at number 4, if I were to add these equations here, negative 3y and 3y become 0. They zero out, which is what I want. And then I'm just going to add. So I have 6x is equal to negative 6. So x is equal to negative 1. Now, how do I find my y value? Well, I just substitute it back into either original. So I can say 4 times negative 1 minus 3y is equal to negative 22. So I have negative 4 minus 3y is equal to negative 22. Negative 3y is equal to negative 18. So y is equal to 6. So again, my point of intersection, my solution to the linear system is negative 1, 6. Again, if I were to graph that, that's where they would intersect. If I want to check it, I go back to each of the originals, substitute those values in to see if I get true statements. Okay, so for number 5, now again, those equations are in standard form. But I can't, when I add them, one of my variables is not going to eliminate. So I have to play around with this a little bit. And I realize if I multiply my top equation by negative 5, that would make that a positive 5y, which is what I want because I have my negative 5y here. And then that y would eliminate. So let's go. Negative 5x plus 5y is equal to negative 20. And then I have 2x minus 5y is equal to 2. That gives me negative 3x is equal to negative 18. So x is equal to positive 6. Okay, I have to substitute that back in. Either equation is fine. I'll do the first one. So I have 6 minus y is equal to 4. So negative y is equal to negative 2. So y is equal to positive 2. So my solution, sorry about that, my solution to my linear system is 6, 2. Okay, for number 6, again, both equations are in standard form, but when I go to add the equations, neither of them, of the variables, is going to zero out. And when I look to see if I can multiply one equation by a number to get opposite coefficients, that's not going to work either. So I'm going to have to work a little bit harder here. I'm going to try to eliminate my y. You could certainly work with the x's. I've just decided to work with the y's. If I multiply the top by 3 and the bottom by negative 2, that's going to give me a positive 6y and a negative 6y, which is what I want. So I have 12x plus 6y is equal to 24. Times negative 2 times each term in there. I get negative 6x minus 6y, right? You see how my y's are going to zero out, is equal to negative 18. So I have 6x is equal to 6, so x is equal to 1. Now let's go back in. Again, either equation, I'll use the first one to find out what my y value is. 4 times 1 plus 2y is equal to 8. So 4 plus 2y is equal to 8. 2y is equal to 4, so y is equal to 2. So my solution to my linear system is 1, 2. That's my point of intersection. All right, looking at our last part of our lesson today, there are a few types of linear systems. So far, we've been working with these. When their lines intersect, they have one solution. Okay. I also have the same exact line would have many solutions. So if I had something like y is equal to 2x plus 4 and y is equal to 2x plus 4, they are the same exact line. So if I were to graph one on top of the other, How many times would they touch? And infinitely many times. That's how many solutions there are, how many times they'll touch. In our first example, they only touched once. That's how many solutions they have, just one. Now, if we look at our third type here, our parallel lines. Parallel lines, they never touch. They have the same slope, but they have different y-intercepts. Different y-intercepts. So for instance, something like y is equal to 3x plus 7, and y is equal to 3x minus 2. Same slope, different y-intercepts. Because they never touch, they have no solution. Let's look at our last few examples. How many solutions are there in the linear system? Now, the first thing, you don't have to graph these to find this out. Just put them in slope-intercept form, okay? So what I did to get us started is I put on number 7, I put both equations in slope-intercept form. Now, as soon as I see that the slopes are different, remember it's y is equal to mx plus b, m being our slope, b being our y-intercept. My slopes are different, so I know that there's just going to be one solution. At some point, they're going to intersect if they have different slopes. And so they're going to touch, and they're going to meet one time. Look at number 8. Now, again, if you want to practice putting equations in slope-intercept form, you can always pause this video and then see how you did compared to the answer that I have when you're finished. So I have y is equal to 2/5 x plus 2. I have the same equation over here. So what does that mean? It means they have many solutions, right? They have infinitely many solutions because they are the same exact line. Last one, number 9. Again, I put this in slope-intercept form. Their slopes are the same. Their y-intercepts are different. This one doesn't have a y-intercept. It starts at the origin. And this one has a y-intercept of -5. So these are parallel lines. There is no solution because they never touch. Okay, great job today. Have a good day.